Alright, in this lesson you're going to be introduced to a new statistical friend. This is one that if you go on and continue your graduate work and take more statistics classes, you'll probably be doing a lot of analysis of variance. In this class we're just going to talk about it conceptually. Analysis of variance, the acronym for it is Anova, analysis of variance. And on this first slide I did a little play on the term Anova. So Anova is actually a car. Apparently there is a cartoon character called Nova. And then if we have any stargazers in the class, you probably have heard of Anova, which is a star that becomes bright and then fades in its brightness over a period of years or even months. So from our perspective, though, we're interested in it from a statistical point of view. And so let's review, firstly, the statistical tests that you already know, and the two that you know deal with performing a t-test. And for our purposes, the t-test tests differences between two group means. And so we've talked about the independent t-test, where our groups are independent of one another, and then we've also talked about dependent t-tests, where the means of the groups are dependent on one another. Well, what analysis of variance does is it tests the null hypothesis between two or more means. So the reality is that if you had only two means, you could use analysis of variance. And again, if you continue your graduate studies, you'll see the link between the t statistic and the f statistic, which is what you calculate for analysis of variance. But for our purposes, we're going to be using this and talking about this really for 3 or 4 or 5 groups of people, looking at differences amongst those 3 or 4 or 5 means. Now, the simplest form of analysis of variance is something called a one-way ANOVA, and I won't really say a whole lot about that right now. We're going to look at an example in a minute, and I'll be coming back and talking about why it's called a one-way ANOVA. And you may be wondering, why is it called analysis of variance? It's called analysis of variance because the variance within an experiment, within all of the members of an experiment, the total variance can be calculated. And hopefully that rings a little bit of a bell for you, because you did a link to the future where we actually called it SST, or sums of squares total. And we're going to talk about that in just a minute. But we know total variance can be partitioned into something called mean square within and mean square between. So again, back to that link to the future, you partitioned, or you calculated the total sums of squares. You calculated sums of squares within and sums of squares between. And so the next step would be, if we were going to do analysis of variance with that data, is to have you go in and divide each of those sums of squares by their corresponding degrees of freedom, and that would turn them into mean square within and mean square between. So that was the purpose of you doing that link to the future. It was because I knew that at some point we would be talking about analysis of variance, and I wanted you to be familiar with and have actually done some partitioning of total sums of squares into sums of squares within and sums of squares between. Now, the variance within the groups is something called experimental error. By definition, experimental error is the failure of identically treated homogeneous experimental units to yield the same results. So as a little bit of an explanation of that, think about if we use good research methods, sorry about that, and we randomly assign members of our experiment to, let's say, one of 4 groups, and each of those 4 groups is going to get a different amount of a drug. And in fact, we're going to have one that gets no drug, so they're going to be our control group. They'll receive a placebo, and then we've got 3 other groups that will get varying milligrams of a certain drug. Once those members have been assigned to that group and they receive their drug treatment, there's probably a part of you that would assume that they would respond identically to each of those 3 or 4 levels of drugs. But the reality, as we might have experienced, is that drugs affect people differently. And so the failure for each of the individuals within a group to for the drug to have the same effect on them is what is referred to as experimental error. We would also call that unexplained variance. variance between the groups could be because of experimental error, so that could be a player there. But what we'd like to think is that it's actually caused or caused by differences due to treatment. So in our drug experiment, that would be differences due to the fact that those different amounts of the drug do result in different responses from the members of the group. Now you might be asking, what is the name of the statistic that you're actually calculating? And you actually end up calculating what's called an F ratio or F statistic. Kind of by definition, again, if you want to think of it this way, the F statistic judges when the difference between the means is above that which would be expected by error alone. And again, we're not going to get into that in a great deal here because I think it's easier to see if you were actually doing some of the calculations. But I do want you to be familiar with the term F ratio. And again, the F statistic is the ratio between MS between and MSW, so between explained and unexplained variation or variability. If there is no differences between the groups, that F ratio would actually be 1. And so kind of stop and think about it. If the differences between the groups is the same as the differences within the groups, then that would be equal to pretty close to 1. Now the F statistic is called an omnibus test because there can be many different outcomes. But stop and think about it. From a t-test perspective, as you calculated the t statistic and you compared it to t-critical, or you looked at the SPSS output from having SPSS do the statistical calculations, and you looked at the p-value, if it were statistically significant and you rejected the null, you knew that the difference was between males and females. Let's say if that's what we were doing for an independent t-test, or if we're doing a dependent t-test, you knew the difference was between the pre-test scores and the post-test scores. But when you're doing and dealing with 3 or more groups, you don't know where those differences lie. And we'll talk about what you would do if you had a significant F-test in a few moments. Now you might be wondering, why don't you just compute multiple t-tests? And the reality is that you could. And so let's say that we have 4 groups of people, which means we would have to do lots of calculations to look at the difference between group 1 and group 2, group 1 and group 3, group 1 and group 4, group 2 and group 3, group 2 and group 4, and then group 3 and 4. So we could do multiple t-tests. The problem with that is that if you are thinking that you're doing each of those tests at the 0.05 level, the reality is that as you do more and more of those comparisons, your actual alpha level starts to rise. So when you did the t-test between group 1 and group 2, so we'll call that the first t-test, you were actually acting at the 0.05 level. And so again, as a review, what you were suggesting is that you're willing to make the wrong decision 5 times out of 100, or 5 times out of 100 any difference that you observed could have happened by chance. But if you move on and do the a t-test to look at the difference between group 1 and group 3, so we're calling that the second t-test, your alpha level raises actually to 0.0975. And so what you're actually saying between both of those tests is that almost 10 times out of 100 any of the differences that you observed could have happened by chance. And then again, if we're looking at the difference between group 1 and group 3, or the third test, look what happens to our alpha level. And then again, the fourth t-test, group 1 and group 4, and again we still have 3 more tests to do. Look what happens to our alpha level. So when we were doing that third test, about 14 times out of 100 the differences we observed could have happened by chance, and at the fourth test, just a little under 20% of the time the differences we observed could have happened by chance. And so that is the reason that you need to use analysis of variance, because what analysis of variance does is it takes all of these combinations or comparisons into account. And if you're working at the 0.05 level, that omnibus test is at the 0.05 level. And so here's our drug example. So the question is, does Thorazine, which is a tranquilizer used to treat psychosis, affect driving ability? And again, what analysis of variance allows us to do is to make all of the comparisons between the groups at one time. Okay, so it is the omnibus test. Instead of making multiple comparisons between each of our groups. And again, when we are able to do that, we can be confident that all of the comparisons are made at the 0.05 level. The good news is, again, if you continue your graduate work and take some more statistics tests, it follows the same steps that we've been working with. And so our null hypothesis, for example, is mu1 equals mu2 equals mu3 equals mu4. And again, what we would hope is that we would reject the null, because if we've gone to the trouble to conduct this experiment, we hope that if nothing else, that these three, if we're in the drug example, are better than doing nothing, which would be our control group, mu1. Again, if we reject the null hypothesis, what does that tell us? Well, what it tells us is that there's some difference amongst these means. The unfortunate thing, unlike the t-test, is that we don't know where the differences is. So because of that, we have to do what are referred to as post hoc tests. Post hoc tests are tests that you would do that identify where the statistical differences are between your means. Another name for post hoc test are posteriori test. So these are tests that you do after the fact. So that's the name, posteriori. And then another name for them is multiple comparison test. So again, in this class, we're only going to be introduced to the concept of analysis of variance. You've done actually a little bit of the work by hand, even back in the first module, but you won't be seeing any more of this from a computational unless you take another graduate statistics test.